Hi and welcome. In this video we're going to be talking about normal distributions, the Chebyshev theorem, and how to find the probability of having an observation with a particular value given the distribution that it belongs to. For that, we will start by looking at the distribution of this sample of people. We know they approximate a normal distribution, and we will proceed by looking at the mean of this group as well as the standard deviation of it, because a normal distribution can be defined by the value of its mean and its standard deviation. However, before we jump into that, we should be defining variance, because that's the value from which we obtain the standard deviation of this group of people. Now, what exactly is variance? A simple textbook answer is variance is the measure of variability from the mean. Let's try to understand this a little deeper and look at the formula. If we grab our sample, the variance would be equal to the sum of each of the observation's values minus the mean of the sample squared. We sum all that up and we divide it by the number of people in the sample minus 1. You may be wondering why in this slide I don't subtract 10 by 1. In here, I don't subtract it because I want to talk about the difference between population variance and sample variance. If this sample of people was not really a sample, but a population, this is, if the entire population consisted of this group of people, we would be using what we call the population variance. In the population variance, we do not subtract the number of people in the population by 1. If we're using sample variance, we do. In here, I have solved the equation just so you can see graphically how it would look like. And the answer is 0.2776. The standard deviation, or the population standard deviation, would be, in that case, the square root of the value of our population variance. However, because we know this is a sample, we should not solve for the equation as we did in this slide. We should subtract 10 by 1. This is the formula that we should have used, or should use, because we are looking at a sample, not at the entire population. That being said, we can move on and go back to this slide we saw earlier, in which we have the normal distribution. Why do we return here? Because right now we know that the mean of our sample equals 6.02 and our standard deviation equals 0.275, I believe it was. I'm just gonna say 27 because I don't remember the rest of the decimals. Because of Chebyshev, or according to Chebyshev's theorem, we do know that any distribution that approximates a normal distribution can be defined by the mean and the standard deviation. And we also know that approximately 68% of the observations in this distribution lie within the first standard deviation, minus 1 standard deviation or plus 1 standard deviation. This is 68% lie on the pink area of this distribution. On the other hand, 95% lie within 2 standard deviations, which means they lie on the purple area. Depending on how conservative we want to go, we could go ahead and say that the two tails that are painted in blue are outliers, because these values are around 5% of the entire sample, and they lie more than 2 standard deviations away from the mean. In other words, the probability of us seeing an observation inside of the sample with that value is of less than 5%, or 5% or less. If we translate that to our heights distribution, this would be a very tall person, and this would be a very short person. How do we make sense of these numbers in a more friendly way? We have the concept of what is a standard normal distribution, which is a little different from the normal distribution we're looking at here. In a standard normal distribution, the mean is a 0 and the standard deviation is 1. This concept is helpful to us because we can standardize our normal distribution into a standard normal distribution and find the relative distance of each of the observations in our normal distribution to the mean. And by doing so, we can look up this value in what we call a C-table to understand the probability of finding each of these values, any of the values, within the normal distribution that we're looking at. Let's go ahead and try to make this a little bit more simple to understand. What we mean by this is that we have a formula that is called the C, to get what is called the C-score. In this formula, we grab any of the observations. We subtract it by the mean of our distribution, and we divide it by the standard deviation of our distribution. The value, or C-score, that we obtain from this formula for any observation is the relative distance between that observation and the mean, or a standardized version of that value. And in the C-table, we can find or translate the C-score to a probability of finding that value. We're gonna go ahead and do a practice example. We have Clarice over here, and she is 6.2 feet tall. In here, we have the mean of the distribution that we observed earlier, and here we have 0.55, because this is the result of finding the sample standard deviation. The operation we did earlier was for the population standard deviation, just so we can talk about the two different concepts. But here we're looking at the sample standard deviation. We solve for this and get this value, which by itself may seem like it doesn't mean much, but when we look it up in the C-table, we can find the probability of someone being shorter than 6.2. Because if this is our distribution and this is the mean, Clarice lies around here, and around 62% of people fall within the green area, green colored area. If we wanted to find the probability of someone being taller than 6.2, we could do 100, I mean 100 minus 62 or 1 minus 62% to find 38%. And we can conclude that there's 38% chance that someone is taller than 6.2 feet tall. But what happens if we want to calculate the probability of Clarice being exactly 6.2 feet tall? There is a little loophole over here. If we subtract 1 minus 62, which is 1 minus the probability of someone being shorter than 62, than 6.2 feet tall, minus 38, which is the probability of someone being taller than 6.2, we would get a 0. We wouldn't get a probability that has, like, we would get 0. And that's not very helpful to us. Why is this happening? Because by doing this, we're calculating the probability that she is exactly 6.2 feet tall. This is that there's an infinite number of decimals after the first decimal. And for someone to be exactly 6.2 feet tall in real life is very difficult. So the probability is very close to 0, if not 0. That's why when we look for probabilities of someone having a certain value, or of an observation having a certain value, when it's a quantitative value, we work in ranges. And if we want to get a number that's helpful to us, we should not be looking at the probability of someone being exactly 6.2 feet tall. We should look for the probability of someone being shorter than 6.2 feet tall, and also shorter than 6.3 feet tall. And this would give us this range right here, which is a probability we can work with, instead of it being 0. Thank you for your time. I hope this was helpful. Stay tuned, and we're going to be talking about hypothesis testing very shortly. Have a great day.